All right, welcome back. This is video 2 of 3. We're going to be covering pipe diameters, reservoir volumes, and QAV in this section. If I haven't said it already, I recommend using the PowerPoint presentations when going over these slides as you listen along or follow along. It just might make things easier for you than using the PDFs that I provide for you. All right, let's dive into it. So, math and hydraulics, right? Um, here you can see I've got a breakdown of how to solve for a reservoir volume. Uh, Reservoirs are typically in cylindrical shape, especially in this example. Reservoirs can come in obviously, multiple different styles, shapes, but in this example, we're going to be using a cylindrical shape. So how to solve for that is diameter squared times 0.785 times the height, which will give you cubic feet. Or you can write it out, diameter times 0.785 times height equaling cubic feet. So to solve for cubic feet, you need to take that diameter. So in this example, the reservoirs are 90 feet in diameter. So 90 times 90 times 0.785 times 40 will give you 254,340 cubic feet. Then you would take that number, plug it in into your problem, and you would get 254,340 times 7.48 gallons per cubic feet, and you're left with 1,902,463 gallons. All right, if you wish to do so, you could try solving these for yourself before I give you the answer, but if you're going to just follow along, then let's get going. All right. A cylindrical or circular tank is 15 feet tall and 40 feet in diameter. How many gallons per foot does this tank hold? So what do we know about this problem? We know that it is 40 feet in diameter. We know that we are only trying to solve for 1 foot of this tank. So that would mean that the height of this tank being 15 feet tall is irrelevant. The unknown that we are actually trying to solve for, though, is how many gallons per foot. So again, diameter times 0.785 times the depth in feet, in this case it is 1 foot, times 7.48 gallons per cubic feet will give us gallons per foot. If you input all of those numbers correctly, you should have come up with 9,395 gallons per foot. Pipe volumes, so much like a reservoir, pipes are cylindrical in shape. The major difference is that reservoirs are given to you in feet, whereas pipes will always be given to you in inches. So you have to solve for that conversion before you can take any other steps. So 8 times 0.785 will give you 0.67 feet diameter. All right. As you can see, our knowns are the length of the pipe, the diameter of the pipe. Our unknown is the diameter in feet and the number of gallons if we were to solve for gallons instead of cubic feet. You can see down at the bottom how I break it down for you, how to convert from inches into feet. If you haven't done so already, you pay attention to that and that will get you there. All right, so let's plug these numbers in. You can see here in this example, I've given you 0.667 feet. If you were to actually divide 8 by 12, you'd wind up with 0.66666666667. However, you could round up, and so you would wind up with 0.667 or 0.67. It will get you really close to the same answer. So it's just the degree to accuracy of which you are trying to achieve. So in this example, I've used the 0.667 times 0.667 times 0.785 times 120 feet, which gives you 41.9 cubic feet. And then if we were solving for gallons in this case, you would take that 41.9 times 7.48 gallons per cubic feet, and you would get 313.5 gallons. All right, here's another problem. If you wish to do so, you may pause the video at this time and solve for yourself. Otherwise, let's continue on and see how we get to the answer of this one. So the question reads, a reservoir measures 210 feet in diameter and has an elevation of 32 feet when full. How many gallons per foot are in this tank? Well, you take 210 feet times 210 feet times 0.785 times 32 feet times 7.48, and you get 8,286,946 gallons per feet. However, that is not the correct answer. We've gone too far, right? As you can see, the question states how many gallons per foot are in this tank. So you can recognize that you've made a mistake and take that same number, that 8 million number, and divide that by 32 feet, and you get the correct answer, which is 258,946 gallons per feet. Or here's another way, you just not make that mistake, multiply it by 1 like you should have, you would have gotten the same answer. All right, second question. If you wish to do so, you may pause the video at this time and solve it for yourself. Otherwise, let's move on. A reservoir is 120 feet in diameter, 32 feet high, and the current water level is 12 feet. How many gallons of water are currently in this reservoir? All right, to solve for this problem, you have 120 feet in diameter, so we need to go ahead and solve for that area. So 120 times 120 times 0.785 times 12 to get us our volume, and we get 135,648 cubic feet. So we take that same number because we are trying to solve for how many gallons of water are currently in the reservoir. We multiply that by 7.48 gallons per cubic feet, and we're left with 1,014,647 gallons. All right, a few definitions for you. These will be used mostly in the video 3 of 3, but I just popped them in here. Not sure why, but anyway, this is where I have them in my presentation. So pressure. Pressure is the measure of height to which the water will theoretically rise in an imaginary standpipe open to the atmosphere. Now, why is this a theoretical? Is because it doesn't take into account gravity or any friction losses, right? Those are other factors that play into effect when pressure is, creating that rise or the height at which water will theoretically rise. You have PSI, which we all know is pounds per square inch, static pressure, which is water that is not in motion, and then you have dynamic pressure, which is water in motion. Head is pressure expressed in feet of elevation. Kind of the inverse of pressure. You have HGL, which is hydraulic grade line. And last, we've got force on there, which is a push or pull measured in terms of weight. QAV. If you're not familiar with it by now, I highly recommend you spend some time learning QAV because this is something that the state loves to put on these distribution exams for problem solving, for your math section. So spend some time with this if you haven't already, if you're not comfortable with it. Otherwise, we're going to break it down and let's get into it. All right, so as we know, velocity, represented by V, is the speed at which water moves. It is usually measured in feet per second in the United States. However, everywhere else in the world, it is meters per second, so it's metric. Quantity, or Q, is the water that flows through the pipe depending on the velocity and the cross-sectional area of that pipe. So your formula would look like this. Q equals A times V. Or if you're trying to solve for velocity, it would be V equals Q divided by A. So here you can see uh, how they're represented. In Q, you will always have cubic feet per second. Area will always be feet squared. And velocity will always be feet per second. So if you look down below, you can see here is an example of, squared area and the feet, or the cubic feet per second. So here in this, what is this, schematic, the drawing, it is 6 cubic feet per second would be the Q. So we know that the V is 6 feet because it's 6 feet here. And then the area is 1 foot times 1 foot. Since this is all squared, it would just be 6 cubic feet per second. So if we were to take some of that information and then plug that into a problem, here's an example problem. You can see you've got a flume that is 2 feet wide and 2 feet deep. It is flowing full of water and has a quantity, and the quantity is measured at 12 cubic feet per second. So what is the cross-sectional area of the flume? It is 2 feet times 2 feet, which will equal 4 square feet. And then we have the velocity, which is 12 cubic feet per second. So if we were to take that and divide that by 4 square feet, you would wind up with 3 feet per second, which is your velocity. So Q equals flow, and that is always represented in cubic feet. Area always equals square feet. Velocity is always feet per second. This is a pretty typical problem that you're going to find on a distribution exam or in your homework, on a quiz, a midterm, final. But here we go. The pipe is 2 feet in diameter and your flow order is 3 cubic feet per second. What is the velocity? So the thing that differs from this question versus the previous two is that now we are dealing with the diameter. So you have to use that 0.785, which will give you 3.14 square feet. We know that our Q is 3 cubic feet per second. So to solve for this one, you would go 3 divided by 3.14. The answer then would be 0.96 feet per second. All right, here's another problem breakdown for you, just to give you all the information. We got an 8-inch pipeline flowing at 350 gallons per minute. What is the velocity in feet per second? So first thing you need to do is convert that gallons per minute into cubic feet per second, right? So to do that, you would take your 350 gallons per minute and you would multiply, well, you cross multiply here really. So really you're dividing 350 uh, by 7.48 times 60, and that would give you 0.78. Or you could use our shortcut that we learned previously and take 350 gallons per minute divided by 449 gallons per minute per cubic feet, and you would get 0.78 cubic feet per second. All right, so at this point we have our Q, but we still need to break it down and convert things further. So if we convert our diameter in inches to square feet, we've got 8 divided by 12, which equals 0.67 feet. And then you would go 0.67 times 0.67 times 0.785, and you get 0.35 square feet. Otherwise, you could do the math a different way because, right, there's always two different ways of doing it. Or you can just take your 8 inches times 8 inches times 0.785 divided by 144 inches, and you would get 0.35 square feet. Same answer. It doesn't matter which one you use so long as you arrive at the same answer. All right, so now we have our Q, we have our A. Now we're able to solve for velocity, right? The V. So in order to do that, we would just take 0.78 cubic feet per second and divide that by 0.35 square feet, and you get 2.23 feet per second. All right, when I do problems, I prefer to put them in pie charts. The reason being is that it keeps things organized for me and it just keeps things a little neater. So that way I can make sure that the numbers I'm getting are being inputted into the correct places. However, these pie charts are useless if the conversions are not done before entering numbers into the pie. So it's important to just go ahead and solve for your area or if you have gallons per minute, solving for cubic feet per second before inputting those numbers onto these charts. So just something to pay attention to. The nice thing about them is that if you are solving for Q, you would just go V times A to equal Q. Or you could do the inverse, and if you have your Q and your A and you're solving for V, it would just be Q divided by A equals V. And so long as you can remember multiplication up and division down, you'll get the correct answer. And it keeps it nice and neat for you. All right, so here's that problem that we solved. You can see how I input those numbers into this pie chart to keep things organized. Feel free to use this method. It's also good for calculating out pounds formulas. I've had several students express to me that they have found success when solving these types of problems by using these pie charts because it keeps things organized for them. So if you're comfortable using a pie chart, feel free to. But if you're still comfortable writing things out linearly, then I recommend doing whatever works best for you. All right. For those of you who wish to solve these problems ahead of time, go ahead, feel free to hit pause on this and run the calculations. Otherwise, let's move on. So you have a 16-inch pipeline that is flowing at 2,500 gallons per minute. What is the velocity in feet per second? So as you can see, we already have gallons per minute, so we know that we're going to have to convert that into cubic feet per second. We have the area, which is the 16-inch pipeline. So we have our Q, we have our A, we just need to solve for V. So really the title of this one should be flipped. It should be V equals Q divided by A up at the top. But we always call these QAV, right? So let's solve for this problem. Right. So let's solve for this problem. All right, so first thing you want to do is solve for your area, which is the 16-inch pipe. So you would divide 16 by 12, and that would give you 1.33 feet. So then you take that 1.33 times 1.33 times 0.785, and you get 1.39 feet squared. And then we use our shortcut that we learned earlier when going from gallons per minute to cubic feet per second. And so we would take that 25 GPM and then divide that by 449 GPM, and you left with 5.57 cubic feet per second. So the last step then to solve for velocity would be to take 5.57 cubic feet per second and then divide that by the 1.39 feet squared, which comes out to 4.01 feet per second velocity. There you have it. There's your answer. Hopefully you arrived at the same one if you solved this for yourself. All right. One last problem before we end this video. Okay, you have a 12-inch pipeline, and the velocity flowing through the pipe is 8 feet per second. What is the flow in cubic feet per second? All right, if you want to hit pause and solve this one for yourself, feel free to do so. If not, let's work on this one together. All right, so we are doing a QAV, right? We are trying to solve for cubic feet per second. The information we've been provided is we have a 12-inch pipeline and the velocity flowing through the pipe is 8 feet per second. So we have to solve for the area first. So to do that, 12 times 0.785 divided by 144 equals 0.785. Some of you may have just, taken 1 times 0.785 and you would have gotten 0.785 as well. Either way works. So now you take that 8 feet per second and you multiply that by the area that we have, the 0.785 feet squared, and you get 6.28 cubic feet per second. All right. And that right there would be your answer, right? Because we've asked what is the flow in cubic feet per second. There you have it. So let's say that you wanted the problem asked you to take this a step further, right? Let's say that we needed to convert this to gallons per minute. What would you do, right? Well, I think we're pretty comfortable at this point. We know that we would take our cubic feet per second times 7.48 gallons per cubic feet times 60 seconds per minute to get our gallons per minute. Or you could just use a shortcut, right? Cubic feet times 449 gallons per minute per cubic feet per second, and you get gallons per minute. All right, let's input those numbers. So 6.28 cubic feet per second times 449 gallons per minute per cubic feet per second. The cubic feet per seconds would cancel out, and you'd be left with your gallons per minute, which would equal 2,819.72 gallons per minute. All right, that concludes part 2 of 3. I hope you're finding some beneficial use out of these and that they're making sense. If not, feel free to send me a message and let me know if you need any more clarification on anything. I'm happy to do so. Uh, with that, I will see you in the next video.